Hello, this is Dr. Strickland. In this video, we're going to investigate the spectroscopy side of carboxylic acids and their derivatives. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the things we will do together in class. So you've actually done a fair amount already with the IR and NMR features of carboxylic acids and some of their derivatives. So this is going to be a lot of review for a fair number of those details. So we're going to walk through the analysis table for these two compounds, and you can see that the structure is already given. And a lot of times when you're looking at a spectrum, you don't already have the structure. In fact, the reason that you want the spectrum is to get the evidence that you need to figure out what the structure is. So we're going to use this structure here to help us kind of Rosetta Stone our way through what we see here in the spectrum. All right, so the first thing you do with a spectrum is to do its analysis table. And then we'll go back and look at the structure and see if what we would have predicted for these different signals is actually what showed up. Okay, so let's give these guys letters. This one, you remember, is not a signal that has anything to do with the structure. This is the reference. This is the TMS, the tetramethylsilane reference signal. And I'm going to put a lowercase letter to the right of each one of these signals. An A for this triplet, a B for this guy, a C for that one, a D for this triplet, and an E for this one. Now, it turns out that there are a couple of inserts here. And so this one goes with that signal there. So I'm going to put a check here because it helps us to see the splitting pattern better. And then we'll do a single check for this one. So about 4.9, so that's this one. All right, so if we go through and just put the information from each signal into this table, A, B, C, D, and E. All right, so I want you to pause the video and put in the information for signals A and B, and then come on back. All right, welcome back. So signal A here, I got the chemical shift as 0.9 parts per million, and I put my units at the top of the column. You can always, with any chart, put the units with every value in the column if you want to. The integration is 3 hydrogens, and I know that because on this spectrum, there are little numbers next to the vertical portion of this integral trace. So 3 for signal A, 6 for signal B, 2 for signal C, 2 for signal D, and then 1 for signal E. And the splitting pattern is connected to the number of peaks in the pattern. There are 3 here in a 1 to 2 to 1 height ratio. That makes this a triplet. And for signal B, I got the chemical shift as 1.2. 6 hydrogens, and this is a doublet. And you can see that clearly from the enlargement that has been inserted right there. All right, so now I want you to pause the video, put in the information for signals C, D, and E, and then come on back. Okay, welcome back. So for signal C, I got 1.65. I decided it was between 0.6 and 0.7 there. And this is a 2 hydrogen signal. Now for its splitting pattern, I can count these 1, 2, 3, 4, 5, 6. That's a sextet. And you have to know the names of these patterns. So make sure that you do. For signal D, I got a chemical shift of 2.2 parts per million, 2 hydrogens, and then this guy here is a triplet. And finally, for signal E, chemical shift is 4.95. And I got that from looking right here at the center of the pattern. I decided it was a little to the left of 4.9. You might think, 4.92 or 3, and that would be fine also. All right, we know it's 1 hydrogen, and from the enlargement here, I can see 1, 2, 3, 4, 5, 6, 7 peaks. That's a septet. Okay, so the great thing about doing an analysis table is you get all the information right where you can see it. And if you didn't already have a structure, this would help you to piece together what carbons were next to what other carbons and how many hydrogens each one of them had attached. So let's go back up here and look at the structure, because sometimes you have a structure and you need to predict what you expect to see in the NMR spectrum. All right, so we've got this signal here, and then we have this signal here, and then there, and there, and there. So let's start here on the right, and we'll just work our way over. So this guy will clearly have an integration of 6. So that's a 6 hydrogen signal. Each one of these carbons that has 3 equivalent hydrogens on it is adjacent to a carbon that has 1 hydrogen. So that's, with the n+1 rule, that's 1 + 1, that's 2. So this is a 6 hydrogen doublet. And because these carbons aren't attached to an oxygen or a double bond or anything like that that might cause a downfield shift, I'm going to say 0 to 1.5 parts per million is where I would estimate that I would find this signal. Now I'm using that table of estimated chemical shifts, the one with the 6 little boxes that go across, and I would encourage you to use that too. Now for signal E, let's see what we've got. 1 hydrogen. Now this carbon is attached to one with 3 hydrogens that way and one with 3 hydrogens that way. So that's 6 + 1, that's 7, that's a septet. And this hydrogen is on a carbon that's also bonded to an oxygen. That's the 2.5 to 4.5 part per million region. All right, come on over here to the left of the carbonyl. This is a 2 hydrogen signal. Its next door neighbor has 2 hydrogens, 2 + 1 is 3. So this is a 2 hydrogen triplet. Because this is an sp3 hybridized carbon that's adjacent to an sp2, this is an allylic position. And that's 1.5 to 2.5. Here at C, we've got a 2 hydrogen signal. It's got 2 neighbors. One this way has 2 hydrogens, that way has 3. So that's 5 + 1, that's 6. This is the 2 hydrogen sextet. And since it's not directly connected to anything that would shift it downfield, we're going to give that the 0 to 1.5 part per million chemical shift estimation. And then finally, this guy here is a 3 hydrogen signal, also a triplet. Also in that just saturated carbon region. Okay, now if you compare this with what you've got down here in your analysis table, they should be identical. And these letters actually do correspond to the letters that we've put into the table, because I just wanted you to be able to see the correspondence. So if you have a structure and you need to predict what you expect the signals to look like in the proton NMR spectrum, you can do that. If you have just the spectrum and not the structure, which is often the case. You can put all the information down into an analysis table, and usually you would have at least a chemical formula and probably an IR spectrum to go with it to help you propose a structure. All right, come on down here and let's look at this IR. The IR is also of an ester, but it's a different ester. You can see here is the ester part, but it's a little different than the one that's above. In fact, the only thing that's different is the alkyl portion that's connected to that sp3 hybridized oxygen. All right, so let's do it the same way. Let's look at the analysis table, and then we'll go up and look at the spectrum. Now, certainly anything that's noted would be worth putting in your table, but also anything that has a tick mark at the bottom. See this little mark there? That one, this one, and then we'll take this one, and we'll take this one. Now the others just mark the presence of other significant signals. If you think that they indicate the presence of a functional group or a particular bend or stretch, you can absolutely put them in your table. I think this one is an sp3 carbon hydrogen stretch because it's in that 2850 to 3000 region, and it's very sharp. Carbon-carbon stretches, carbon-hydrogen stretches, often very sharp because they can't do any hydrogen bonding, as opposed to like OH stretches, which are very broad. And you can see in these carbon-oxygen stretches, either with the double bond or the single bond, there's a little bit of roundedness, not a lot, because this oxygen is a hydrogen bond acceptor. Can't be a hydrogen bond donor because there's no hydrogen attached to it. But it does give it, I think, that little bit of roundedness. So in an IR analysis table, we need the location. And I estimated this one at 2980. Identified it as an sp3 carbon hydrogen stretch. Anytime you report a carbon hydrogen stretch, you must include the hybridization of the carbon, because that's what sets the range. The range is very different for sp3 carbon hydrogen stretches versus sp2 versus sp. Okay, and so the expected ranges just confirm my assignment of what it is given its location. So I said 1780 for the carbon oxygen double bond stretch. These show up in the 1650 to 1780 region. And then a couple of carbon oxygen stretches. One at, I estimated at 1195 and the other at 1100. Anytime you have an sp3 hybridized oxygen, it's bonded in two different directions. And particularly with something like an ester, where this one is bonded to the sp2 carbon of a carbon oxygen double bond, there's going to be another resonance contributor in here, which will make this carbon oxygen bond very different in strength from that one. So very often you'll see two different signals when you're talking about an ester. Both in the same region, in this 1050 to 1250 centimeters to the -1, or wave numbers. But one much farther to the left than the other, and the one that's farther to the left is the stronger of the two. That would be this one as opposed to that one. All right, so I want you to answer the question at the end of this video, and then I'll see you in class.